The last video in this series has to do with finding the maximum or the minimum of a function. I'm actually only going to talk about finding the maximum of a function. The minimizing is essentially the same, except to minimize we'll look at convex functions rather than concave functions. So let's suppose that we have a concave function. What I want you to do is think about climbing a hill. If you start climbing the hill, when you get to the top of that hill, there's a tiny little part that's going to be as if it were flat. So the question we're really asking here is, for what argument to this function do we reach that flat part? In a mathematical sense, we're really asking, at what value of the argument can we no longer increase the function? So the way we write down formally the question that we're asking is, what is the solution to this maximization problem? You've got a function f that gives you a value for each number. So to solve this maximization problem is to find the x that gives you the highest or the maximum f of x. Like I just pointed out, what we're really going to do is to look for the flat part of the hill. F is a concave function. We're going to look for the little flat part. In other words, we want this x where the derivative is 0. So we want x such that the derivative of f at x is 0. Let's do an example. Let's take this function f of x, which is 1/2 times x minus a half squared. The objective is to find the value of x that gives us the highest value for 1/2 of x minus a half squared. We do that by taking the derivative of f with respect to x. If we did so, 1/2 x minus a half squared. So the derivative of this is 1/2 times the derivative of this part, which is 2 times x minus a half. We're using the power rule here. The 2's cancel, and so we're left with x minus a half as the derivative. So if we want to find the x that gives the maximum value, we just set this derivative equal to 0. And if we solve for x, remember we've seen how to manipulate equations to solve for a given variable. So if we want to solve for x, we just add a half to either side, and we get the solution 1/2. One convention that we often use is to use a little star or an asterisk to represent the solution to the maximization problem. So in this case, the x that gives us the highest value of 1/2 times x minus a half squared is 1/2, so we represent that solution by x star. That was pretty easy for a function of a single variable. What if we have two variables? So we would write the maximization problem as choose x1 and x2 to maximize f of x1 and x2. If the partial derivative with respect to x1 is 0, that means a tiny change to x1 isn't going to increase the value of f. Similarly, if the partial derivative with respect to x2 is 0, then small changes in x2 aren't going to change the value of f. So the idea of finding the point where the function is at the top of the hill, or it's like a little flat part, is to look for the point where the partial derivatives are both 0. So to find the pair x1, x2, such that we've maximized the value of f of x1, x2, we just need two things to be true. The partial derivative of f with respect to x1 is 0, and the partial derivative of f with respect to x2 is 0. These are what we call first-order conditions. In particular, notice that we've got two first-order conditions, one with respect to each of the variables that we need to choose in order to maximize the function. So the first-order conditions give us two equations and two unknowns, and we can use those to solve for the optimal value of x1 and x2. Let's do an example. Here's our function that we're trying to maximize. It's a function of two variables, x1 and x2. It's 1/2 x1 minus 4 squared plus 1/2 x2 minus 9 squared. So we want to choose x1 and x2 that give us the highest value for this. What are our first order conditions? Remember, the first order conditions are the partial derivatives with respect to each of the variables. So the partial derivative with respect to x1 is the derivative of this part. If we treat x2 as a constant, then this whole thing is a constant. So when we take the derivative of this with respect to x1, this part is 0. And the derivative of this part is 1/2 times 2 times x1 minus 4. The 2 and the 1/2 cancel to give us 1, and we're left with x1 minus 4. We do a similar exercise to calculate the partial derivative with respect to x2. The first part is a constant because x1 is treated as a constant when we're trying to calculate the partial derivative with respect to x2. And when we take the derivative of this with respect to x2, it's 1/2 times 2 times x2 minus 9. The 2 and the 2 cancel again, and we're left with x2 minus 9. So we've got two equations and two unknowns. These equations turn out to be very easy to solve, To solve for x1, we just add 4 to either side. We add 4 here, add 4 here. This -4 and this 4 cancel. So we get the optimal x1 is just 0 plus 4, which is 4. Remember, the fact that this is the optimal x1 we represent by using this asterisk. Similarly, we just add 9 to either side to find that the optimal x2 is 9. So that's how we solve for the maximizing x1 and x2. We just write down the first order conditions, which give us 2 equations in 2 unknowns, and we solve them for the 2 unknowns. One important feature of this particular maximization problem that we looked at is that you could pick any x1 and any x2 you wanted. So we call this an unconstrained maximization problem. There's nothing to constrain your choice of x1 and x2. But you can't always just pick whatever x1 and whatever x2 you want to pick. In a lot of economic problems, we're going to have constraints. For instance, you might have $10, but then apples cost $1 and bananas cost $2. Is it reasonable to say that you could buy 15 apples and 20 bananas? No, the 15 apples are going to cost you $15, the 20 bananas are going to cost you $40. So altogether you're spending $55, but you've only got 10. So you can't just pick whatever. So we're going to be interested in the types of maximization problems where you are constrained in what you can choose. Let's suppose that the constraints are in the form of a function h. So you might have a constraint that says you can pick x1 and x2 such that, that's what the ST stands for, their value according to h has to equal some fixed amount z. In the example that I just gave you with the apples and bananas, if x1 were apples and x2 were bananas, what apples and bananas can you pick? If apples cost $1 each, how much does it cost to buy x1 apples? Well, just x1. If bananas cost $2 each, how much does it cost to buy x2 bananas? Well, it's 2 times x2. So if you bought x1 apples and x2 bananas, in total, that's going to cost you x1 plus 2x2. So h here gives us the cost of consuming x1 apples and x2 bananas. So what is z here? Z is the amount of money you had. The cost has to be exactly equal to the amount of money you've got to spend. And we said that was $10. So this constraint, for the example I just discussed, is that x1 plus 2x2 has to equal to 10. Find the amounts of apples and bananas that maximize the value f of x1, x2, such that this equation holds true. So that's what a constrained optimization problem is. The easiest way to deal with these types of optimization problems is to use this equation, manipulate it to solve for one of the 2 variables in terms of the other, and then substitute that in to your original optimization problem. Now you've got an unconstrained optimization problem. Again, going back to our example, since h of x1 plus x2 is x1 plus 2x2, and we want that to equal to z, which is 10. So we've got this equation, x1 plus 2x2 equals 10. So what we can do is we can solve for x1 in terms of x2. So subtract 2x2 from either side, x1 plus 2x2 minus 2x2 equals 10 minus 2x2. These plus and minus 2x2's cancel, so we get x1 equals 10 minus 2x2. So this is how you can solve this equation that gives us the constraint for one variable in terms of another. So we solve for x1 in terms of x2, and then we plug that back into our function. So then we solve the following maximization problem. Choose x2 to maximize f of, remember x1 is 10 minus 2x2, 10 minus 2x2, and x2. So you've got this maximization problem of a single variable, and it's unconstrained, and we know how to do that. More generally, we take this equation that gives us our constraint, h of x1, x2 equals z, solve for one of the 2 variables in terms of the other. So we solve, in this case, we're going to solve for x2 in terms of x1. So it's going to give us some function of x1. We substitute that back into our function f. So now we're going to choose x1 to maximize f of x1, r of x1. This is called the substitution method, and it's going to be good enough to do most of the things you're going to do. The more sophisticated method of doing this is to use the Lagrange method, but we're going to keep it simple here. So let's do an example. Let's suppose we have to maximize the log of x1, x2, and we're subject to the constraint that x1 plus x2 equals some z. Remember, z is a constant. So we're going to solve for x2 in terms of x1 and substitute that back in. So if we look at this equation, we can subtract x1 from either side. So the left-hand side will just be x2, and the right-hand side will be z minus x1. We're going to substitute that back in here and then get rid of the constraint. So if we substitute that, we're left with log of x1 times z minus x1. And so we're going to solve the unconstrained maximization problem of a single variable, where we want to find the x1 that maximizes log of x1 times z minus x1. So we can write down the first order condition, which is the derivative of log of x1 times z minus x1 with respect to x1. To do so, let's use a commonly known fact about the log. Log of x1 times z minus x1 is the same as log of x1 plus log of z minus x1. Now we can use the addition rule. The derivative of this part is just 1 minus x1. The derivative of this part, well, first notice that we've got a negative sign in front of the x1, so we're going to use the chain rule. So we're going to get negative 1 times 1 over z minus x1. So it's negative 1 over z minus x1. So we have the following derivative of the function that we're trying to maximize. And we set that equal to 0 because that's what our first order condition is. Remember, we're looking for the top of the hill. So let's solve this. So we're going to add 1 over z minus x1 to this side, and we'll add it to this side. The 1 over z minus x1 and the minus 1 over z minus x1 cancel on the left side. So we get 1 over x1 equals 1 over z minus x1. If you recall, when we manipulate these equations, you can do whatever you want to one side as long as you do it to the other side. If we take the reciprocal on both sides, we get x1 equals z minus x1. Now we can add x1 to both sides. The negative and the plus x1 cancel. So we get 2x1 equals z. Divide both sides by 2. The 2's cancel. So we get x1 equals z over 2. That's our optimal value of x1. So to finish, we just need to find the optimal value of x2. And how do we do that? Well, we go back to the equation that we came up with when we solved for x2 in terms of x1. We just plug in our optimal value of x1 to get the optimal value of x2. Our optimal value of x1 is z over 2. So the optimal value of x2 is z minus the optimal value of x1. So it's z minus z over 2, which is z over 2. And that's how you maximize a concave function of two variables. That wraps up our refresher course on the math you'll need for your courses. Feel free to ask your instructors any questions you might have.